What is this for? No, this doesn't help. Oh, I think it's like that we're connected to this instead.
Yeah, just try.
But it doesn't connect, like the heads are different. So let me plug it in here. No, I think it's just wait, more inputs. Wait, which one is this? Laptop?
You stay on laptop. Display.
Image is on the.
Oh,
well, okay. Okay, guys.
Test it.
Yeah. Okay. Cool. Okay, we're about to start. Guys, should I just stand? I just stand.
Do whatever you want.
Okay, sure.
Right.
All right, so we'll start part 1 first. Presented by us 3. Part 2 will come tomorrow from 4 to 6. Hopefully there's no delays tomorrow. Okay, so here's the attendance form. We really appreciate if you can scan it first. Yeah, just because it's good for our internal record. Yeah. We have to inform. All right. Okay, now that everyone's scanned the attendance form, we can start. Oh, we have another form actually.
No, this is just an advertisement. So in 2026, at the start of the year, we'll start our annual peer mentoring program. And so it's an opportunity for, as a peer mentor, it's an opportunity to kind of get with a group of first years and kind of guide them throughout like their start of uni. It's kind of just like weekly activities and bondings just to try and, get them acclimatized into the like uni atmosphere. It's really rewarding and we really highly recommend. We're currently recruiting mentors. And so, yeah, there's just the QR code if anyone's interested.
Yep, so great leadership opportunities. We'll come back to this if anyone's interested at the end. But anyways, we'll start our revision seminar today. And we're covering parts 1 and 2 only. Tomorrow will be parts 3 and 4, but basically up to Marira's theorem for today. Okay, so starting with part 1, intro to complex analysis. We're going to look at some basic set definitions as a recap, and then go on to exponentials and logarithms, and then finally some complex integrals. So starting with basic rules and ideas for complex numbers, I'm sure we all know that complex numbers can be written in different forms. The most common one is z is equal to x plus iy, which is splitting it into imaginary and real parts. And second is using polar form or Euler's form, which is this. You can write it as a modulus times e to the power of I theta, where theta is the angle that it makes with the x-axis or the real axis. And just note that normal rules of addition, multiplication, subtraction all hold. Only thing with division is we usually want to simplify the expression by making denominator purely real. Some important ideas. This identity is quite useful. You end up using it a lot in simplifications, so it's just something worth noting. Another thing is that principal argument, by definition, is chosen such that the argument is between the angles of negative pi to pi by convention, where it's inclusive of pi but not for negative pi. Okay, right, so going on to inequalities, we have 2 important inequalities that we end up using a lot in this course. The first one is triangle inequality, which is really simple. It's basically you just draw vectors, let's say w and z, and w plus z is going to be basically the diagonal made from w and z. Okay, I don't know why there's breaks right now, but yes, basically it's saying that the third side of a triangle is going to be less than or equal to the sum of the other 2 sides, which is what this triangle inequality is saying. And from the triangle inequality, we actually have something called the circle inequality, or sometimes referred to as the reverse triangle inequality, a complex number w and a complex number z, and basically take the absolute value of the difference between them. That's going to be less than or equal to the modulus of the complex number w minus z. So you can think about this as having basically two complex numbers. Why is it called a circle inequality, by the way? It's basically like having two complex numbers on the circle and then trying to draw out w minus z, and then comparing that to the modulus of w and z, the difference between them. You can try to draw the diagram yourself, but basically you're going to prove something analogous to modulus w is less than equal to modulus w minus z plus modulus z, which is basically just the triangle inequality again. Okay, and then let's actually look at an example. So given that modulus of z is greater or equal to 2, we wish to prove this inequality. So a tip with doing these inequalities is usually you look at the sign to determine which inequality you want to use, like if you want to use triangle inequality or circle inequality. And in this case, the sign is going to be less than equal to. And because we know that for the triangle inequality, your signs usually is already less than equal to, but given that this is a fraction, we're actually going to flip the sign, which is why if you end up using the triangle inequality, you should be getting a greater or equal to sign instead, which is why here we're not going to use the triangle inequality. So we're going to use the circle inequality instead. And just note that even though it's z to the power of 4 plus 1, we can actually write it as z to the power of 4 minus negative 1, which is another very common trick. And then once you apply the circle inequality on this is going to be greater or equal to, less than equal to the modulus of z to the power of 4 this is greater or equal to. Yeah, this is greater or equal to the modulus of z to the power of 4 minus modulus of negative 1. Okay, and this is a greater or equal to sign. So basically, I'm just starting from the right-hand side of the circle inequality, and then I can just simplify this. So this is greater or equal to the modulus of z to the power of 4 is going to be greater or equal to 2 to the power of 4, right, which is 16, and then minus 1, which is equal to 15. So I know that z to the power of 4 plus 1 modulus is greater or equal to 15. So if I take 1 on that, where both sides are positive, I know that 1 over z to the power of 4 plus 1 is going to be less than equal to 1 over 15. So I just take the reciprocal of both sides and flip it. And this is how you can do problems like this. Right, here's the working out for a reference. And then moving on to some set definitions. So first of all, we have open balls. We didn't include punctured open ball. Basically, the only difference is whether you're including the center or not. Types of points. There's 3 types of points that we have, which is either it's an interior point in a set, or it's an exterior point, or it's a boundary point. So if it's interior, you can think about it as you have a set that's basically, what's it called? That doesn't contain any of its boundaries. So basically, whenever you take a point in the set, you can always draw a circle with a radius that you choose to be small enough such that this entire circle is contained within the set as well. So that's what defines an interior point. And an exterior point is just something that exists. Essentially, you draw a circle around it such that it's always falling out of the set. Boundary point is just exactly lies on the boundary of the set. Okay, so some other set definitions. A set can be open, closed, or neither. If it's open, then every point is an interior point, as defined above. If it's closed, then it contains all of its boundary points. Or similarly, you can also think about it as the complement of the set is open. So closure of the set, which is notated usually using this bar notation, is just defined as the set of all of the points that's contained within that set, plus all of its boundary points. If a set is bounded, that just basically means that it can be like you can draw a circle of a finite radius that contains this entire set. If it's compact, that just means it's closed and bounded. And if it's a region, you can notate it as basically an open set, let's say S union some other set that contains none, some, or all of its boundary points. So basically, you can write it as a union of those two sets, where this is going to be an open set. This is a bit sad that the drawing is a little hard. Okay, so types of arcs. We have polygonal paths, which is basically, just think about it as a set of finite line segments that connects points, where a closed polygonal path is then you start at end at the same point. And a simple path is basically when you don't cross yourself. Okay, so then based on this, we develop 3 other definitions, which is a set can be polygonally path connected, or PPC, if basically for every 2 points in the set, you can find a polygonal path that connects those 2 points, which along this path, every point along this path is also within the set. If it's simply polygonally connected, that just means it's polygonally path connected, and also the interior of every closed arc is also a subset of S. So what that means is, for example, if something is not simply polygonally connected, it will, for example, look like this. If you look at this set, if you draw a polygonal path, let's say like this, the interior of this path is actually not all contained within the set S, which is why this set would be considered as not SPC. And finally, it would be defined as a domain if it's both PPC and open. Okay, so let's look at an example where we try to determine if sets are open, closed, bounded, compact, and so on. Right, so we're given 4 sets, S1 to S4, and it would be really beneficial when you guys are given something like this to just draw it out, because that helps to visualize it. So if we draw out S1, S1 is defined as the area inside the circle of radius 1 centered at 0. So draw a brief sketch. This is S1. And then we can also draw S2. So S2 is defined as the region between the lines x is equal to 0 and x is equal to 1, not inclusive of x is equal to 1. Where if this is the real axis, this is the imaginary axis, then S2 would look like this. You can draw a hollow circle there. So this is S2. S3 is just the single point 1 plus I, so we're not going to draw that. S4 is basically like the donut shape, where you're taking the area between the circles centered at 0 with radius 1 and centered at 0 with radius 2. So like this. This is not to scale. So this is S4. And then we're going to analyze if it satisfies any of these set definitions. So first of all, looking at set 1, is it open or closed? We know that this set, because it doesn't contain its boundary points at all, every point is going to be interior. So this is open. And it's obviously bounded because it's entirely contained within the circle of radius 1. So this is bounded. Is it compact? Well, if it's closed and bounded, it's compact. But in this case, it's not closed, right? So it's not compact. Is it polygonally path connected? Because if you look at 2 points and try to draw an arc, you would realize that arc would always contain points that lie only within the circle. So it is polygonally path connected. It doesn't contain any holes. So that means you're not going to create any holes if you draw a polygonal path, which means it's also SPC. Is it a region? So basically, definition of region is sometimes a bit confusing, but you can just think about it as if it contains any interior points or not. Because if it's an open set that has interior points, then it's most likely to be a region. If it doesn't have any interior points, then it's not going to be a region already. So in this case, because it's an open set and pretty much all of the points are interior, so it is going to be a region. Okay, so basically you can write it as just S1 union none of its boundary points. And then looking at S2, if we look at this set is actually not open because not every point is interior. For example, any point that lies on this line is not an interior point, right? Is it closed? It's also not closed because it doesn't contain all of its boundary points either. So this is neither open nor closed. So this is just neither. Is it bounded? It's also not bounded because imagine that this region can extend infinitely both ways, upwards and downwards, right? So it's not bounded. Is it compact? If it's not bounded, it's already not compact. Is it polygonally path connected? Now, if you draw a line from any 2 points, like from one point to another point within this area, you would realize that it is going to that line is going to be contained within this this region. So this set, so it is polynomially path connected. It's also simply path connected because it doesn't contain any holes. And is it a region? Well, a region requires the set to be open. So if it's not open, it's already not a region. And then looking at S3, so S3 is the single point. So by definition, a single point doesn't contain any interior points, so it's not open. And it's also not closed because it also doesn't have any boundary points either. It is bounded because you can always draw like a circle to bound that point. It's not compact because it's not closed. It's polygonally path connected by definition. It's also simply path connected. Actually, I think our definition it's not because you don't have any 2 points within the set. So you can't really draw any polygonal arcs. So therefore, it's also not simply path connected, and it is also not a region since it's not open. And finally, S4, it is a open set because it contains all of its every point that's contained is interior. It is bounded because it's bounded by the circle with radius 2. It's compact because it's open and it's not compact because it's not closed. And it is polygonally path connected, but it's not simply polygonally path connected because if you remember the example that we looked at, if you create an arc around this, you're going to create some holes, and it's therefore a region because you can draw it as an open set with none of its boundary points. So here is an overview of the answers. You can, yeah.
I thought we defined closed as the complement of the set is open, right?
Yes, pretty much. But also you can think about it as the set containing all its boundaries.
1 point from the complex plane, shouldn't that be an open set?
If you take out 1 point from an open,
I take out 1 point from the complex plane.
Yeah.
Without 1 point, isn't that open?
Well, if it's open, that 1 point, there has to be an interior point, but you cannot. So how do you define an interior point? Is if you can draw a circle around it with radius small enough such that the circle is also contained within the set. So if you think about a point,
say the complex numbers without 0, for every point I can draw a small enough circle.
But the small enough circle cannot have radius 0. So for a point,
the complex numbers without the point 0, right?
Yeah.
And I take any point z, and I draw a ball around z with radius modulus of z half. Then that ball is going to be inside the complex plane without 0, right?
You want to repeat? So you're basically trying to ask if a point itself is an open set or not.
It's closed because the complement is open.
An open point.
Just 1 point is closed.
But how?
The complement is open.
So technically, by definition, though, for just the definition of an open set, just the definition of a closed set, it has to contain its boundary points.
Yeah, and the point is the boundary point of the set, right? Because for that point, any radius, any ball I take has 1 point inside the thing, which is the point itself, and 1 point outside, which is any point other than that point. What is it? The empty set and the entire complex plane, they're both more like a pedantic. Yeah, I know. Empty set and whole plane is closed and open. I know that, but I'm asking specifically about one set with 1 point. A set with 1 point.
So a set with 1 point is defined as neither open or closed.
But the complex plane without 1 point is open, right?
That's defined a little bit loosely depending on what you refer to.
Definition, from interior points, I can for every point in C without 0, all the inverted.
So the thing is, yes. So the thing is, if you just apply your definition of open and closed, sets without considering the closure, then a point itself would not be considered as either open or closed because we don't really say that an open point itself has boundaries points.
Why not? That's what I'm asking because
that's really just by definition.
For any small number, for any epsilon around the ball, if I take the basically the idea is that if I intersect the ball with the set, it's going to be not the empty set.
which in my case, so like in your definition right there, if S is just 1 point, then for every epsilon, B, and then like let's call the point X or Z, whatever, B, Z, epsilon intersected with the set is going to be just Z. And that's not going to be the whole ball since the ball contains more points than just Z, right?
Yep.
So per the definition, that is the boundary point. Like we can just plug in S is equal to the set that just contains Z, and we want X is equal to Z, right?
Yes,
So
but
that's the boundary point.
okay.
Okay, guys, just to clarify, this is what Alessandro said. A point is closed, bounded, compact, PPC, SPC.
Yeah, exactly. But you just in your answer sheet, it's
Oh, that's all right. Sorry. This is actually, I think it's because this was like a question from last year where they used a different definition, I think. Because yeah, I think like for complex analysis set definitions, it varies from textbook to textbook. So I think this year we're adapting the definition of a point being closed, but I think last year it was still defined as not being closed. Does that make sense? Yeah. Okay.
Also, and like just think, because like you said, compact is yes, and for compact we need closed and bounded, right? So
yes. So yeah, so if it's closed and bounded, then a point would also be considered as compact.
Yeah, but if it's compact, if the set is compact, then it's closed and bounded.
Yes. So this is a typo technically. So it's supposed to be no according to our definition from last year.
Yeah.
Yeah. Okay. Cool. Sorry for the confusion, by the way. Yeah, but just remember for the set definitions, I would recommend that you go back to revise like what Anna said during her lecture, because that's the definition we're using for this year, the most updated one. Okay, and then moving on to, but that's probably the only point of ambiguity in the course. And then moving on to functions, complex functions. Complex functions basically just its domain or range is a subset of the complex plane or the entire complex plane. Right, so something within complex functions that we're interested in is called fractional linear transformations. So we know that these functions is of the form like this, where basically every fractional linear transformation or FLT is going to translate a circle or a line into another circle or a line within the complex plane. So basically, whenever you're given a fractional linear transformation, you can expect that if you're transforming a circle or a line, you should be getting a circle or a line as well, which helps to solve some questions in easier ways. So let's look at one example. We're going to consider the FLT of t is equal to w, which is equal to 1 over z plus I. And we want to find the image of the line defined by basically 3x plus y is equal to 1 under this mapping. So usually what we do in these questions is you can always let z is equal to x plus iy and then express w in terms of z in terms of w, and then let w be equal to u plus iv, and then basically just doing some algebra to find their imaginary and real parts in terms of uv, and yeah, and then you can just plug in your x and y. So that's what we've done here. Basically, when you rearrange this equation, you're going to get z is equal to 1 minus iw over w, and then you can just plug in the u plus iv and simplify, which we're not going to do here for the sake of time. And then just compare its imaginary and real parts. So if you compare real parts, z, which is equal to x plus iy, is also equal to this expression. So you know that x must be 1 over u squared plus v squared, whereas y must be this, which is the entire imaginary part. And then what you can do is, since you're given that originally 3x plus y is equal to 1, that is still going to apply. So you can just plug in your x's and y here, and 3 times x plus y is going to give you 1, and start simplifying the expression to get an equation in terms of u and v. So in this case, you're going to realize that this is going to map it into another circle with center at 0, negative 1 on 4, with a radius of 5 on 4. Yeah. So this is just a common trick that you can use, usually letting z be equal to x plus iy after a lot of algebra normally works. But there are also simpler ways. In some cases, when you are not in the case of when you're specified with a real and imaginary relationship, but in other cases, you can usually rearrange like w. You can rearrange z in terms of w and then just plug in the equation for w and simplify. Okay. And we have another example, actually, yeah, we have another example, which is just considering the image of 3 points rather than the entire, right, finding an overall rule. So in this case, if you have t is equal to w, which is z plus 1 over z plus I, and you want to find the image of this particular circle under this transformation, what you can do is just take 3 points in the circle and then find where these points land. So if you know, if these points happen to form a line, then you can expect that it's going to map this set into a line, and you can find the equation of the line easily just by like setting up your own variables and then finding a, like you can let y equal to ax plus b, and then finding your a's and b's just by plugging in these numbers. But if it ends up being a circle, well, then you can also do it the exact same way, where you can find the radius just by checking the boundary points to the center, the distance from the boundary points to the center. So this is what we've done here. We found where the points 0, 1 minus I, and negative 1 minus I land after this mapping, and it corresponds to these points. So then what happens is we know that if you check yourself, this is actually not going to form a line because no A's and B's is going to make an equation that that maps all of these 3 points to their corresponding points. In which case, if it's not a line, then it must be a circle because we're dealing with FLTs. So we know that if it's a circle, then you can see where its center lies, and you can find its corresponding radius, and then you can just directly write out the formula for the circle. So this is just a relatively easier way of doing questions where you don't have to go through all of that algebra, and you can just simply plug in points to check if it maps it to a circle or a line. Okay, and then that is it on set definitions. So we're going to look at limits and differentiability and just some basic things. So limits are defined pretty much the same way as they are in Math 1A and 1B, where basically limit exists only if the limit attains the same value along different paths. So it's not existing, it doesn't exist if along different paths you get different values for the limit. And if we want to rigorously prove that a limit exists, then you use the epsilon delta definition, which is basically identical to 1A and 1B. So basically, a limit is just a value that the function approaches whenever you are setting a random restriction on your z. So along the x-axis, you can think about it that way. So basically, as x gets bigger and bigger, your y is getting closer and closer to some value when you set an arbitrary restriction on your x. Okay, so we can look at an example, which is proving that this particular limit doesn't exist. So when you're trying to prove a limit doesn't exist, it's very helpful to think about that when you trace along different paths, you're going to get different values, which means in this case, it's beneficial to use Euler's form, because in Euler's form, when your z approaches 0, this r, which is the modulus, is always going to approach 0. Whereas if your theta varies, then you could be potentially getting different values, which is why we want to consider Euler form in this case. So if we use the Euler form for z and then we plug it in, imaginary part of z is just going to be r sine theta, whereas z you can just plug in r e I theta. So you're going to get this expression for the limit. And after simplification by dividing by r, we get this is actually equal to sine theta over e to the power of I theta. So let's take, for example, theta is equal to 0, then this limit is going to become 0. Whereas if you take theta equal to, let's say, 90, your limit is going to evaluate to 1 over I, which is negative I. And clearly, these are different values along different paths, which means this limit cannot exist because it's not the same value. Okay, and moving on to continuity. Continuous is basically when you approach the point from both sides and the limit of that point is just equal to the function value of the point. So yeah, so sums, products, quotients, and composition of continuous functions are always continuous where it's defined. Okay, so another example, we want to prove that this function, which is the imaginary part, is continuous for all complex numbers, which basically just means you want to use the rigorous epsilon delta proof. So you want to prove that the limit of z as z approaches any random point in the complex plane of this function is just equal to the function value at that point, which is equivalent to saying that you want to find this you want to find an epsilon such that epsilon and delta such that this inequality is satisfied. So because if we compare the right-hand side of those two inequalities, we realize it would be very beneficial if you just choose delta be equal to epsilon, and then we start with this. So we start with, let's say z minus 0 is between 0 and epsilon. In that case, fz minus f of z0 would just be equal to this, where we use the definition of the function, which is also equal to imaginary of z minus z0, which is going to be less than equal to z minus 0 modulus. And why is that? Is if you think about this as a complex number, then the imaginary part of that complex number, the modulus of the imaginary part has to be always less than the modulus of the overall complex number, which is going to be less than delta, which is then equal to epsilon, since we chose delta be equal to epsilon, in which case we've proven that this limit exists. And so therefore, fz is equal to imaginary z is going to be continuous in the entire complex plane. For differentiability, basically it just has to satisfy this first principle. And differentiability implies that it has to be continuous at that point, because this has to exist. So these has to exist, which is why if a function is differentiable, then it's always continuous, but continuous doesn't imply differentiable. And differentiation rules is the same as those for real numbers. Okay, so Cauchy-Riemann equations, which are a pretty important part of this. So basically, a function is differentiable at an interior point, which implies that it's in an open set, if and only if the partial derivatives of u and v, which is its imaginary and real parts, correspondingly, all exist and are continuous. And this satisfies this particular equation, where if you partial diff u with respect to x, that's going to give you, that should be equal to if you diff v with respect to y. And same thing, if you diff u with respect to y, you should get that should be equal to negative if you diff v with respect to x. And you can just find the derivative then, if it exists, by diffing both u and v with respect to x. So here are some examples where we want to determine where are the following functions differentiable. So looking at f1, which is equal to z times modulus z squared, if you want to verify that it's differentiable, then it has to satisfy these Cauchy-Riemann equations, right? So basically, you want to find the expression for its real part and imaginary part functions. And in this case, we normally let z be equal to x plus iy to do that, such that you can find the real and imaginary functions. So if z is equal to x plus iy, then z times modulus z squared. It's a bit hard to write, so I'm just going to jump to the outer bow solution. But it's basically the same thing, so you just plug in z is equal to x plus iy and then simplify, and you should be able to get this expression, where this is corresponding to u and then this is v. So you want to verify that partial diff u with respect to x is equal to diff v with respect to y. So basically, you just want to find all of the first partial derivatives and then check if they're equal to each other. So if you look at this du on dx and dv on dy, they are already, if you want this function to be differentiable, then they have to be equal to each other, right? Which basically means that you need to equate 3x squared plus y squared to 3y squared plus x squared, which is going to simplify it down to 2x squared is equal to 2y squared, which basically means x squared is equal to y squared, or x has to be equal to plus minus y. That's your restriction 1. Your other restriction is on du on dy and dv on dx. So these two have to be the opposite of each other, which basically means 2xy has to be equal to negative 2xy, which just means that xy has to be equal to 0. So xy being equal to 0 implies either x is 0 or y is 0. But because we have the other restriction, which is that x has to be equal to plus minus y at the same time, then you know that they must be equal to each other. So therefore, both x, y has to be 0. And the solution is just f is only differentiable on the point where it's on the origin. And for the second example, which is defined by f of x plus iy is x to the power of 3 plus iy to the power of 3, this function is much nicer because you don't have to plug in the x plus iy already. You can just directly use the result. So this is u and this is v, and you diff u and v with respect to x and y. So if you diff u with respect to x, you're going to get this. With respect to y, it's just 0 because u is just completely in terms of x. It's the same thing if you diff v with respect to x and y. And we realize that because du on dy is already equal to negative dv on dx, the only restriction is just that du on dx has to be equal to dv on dy, which is just saying that 3x squared has to be equal to 3y squared, which is saying x squared has to be equal to y squared, or x has to be equal to plus minus y. So for this function, it is only differentiable along the lines y is equal to plus minus x on the complex plane. And our third function, which is defined by this, this is slightly like unconventional because it has an absolute value, but pretty much we can differ the same way, where if you realize if you want to diff an absolute value, that just splits it into two cases, right? Which essentially is saying it's going to be equal to x over absolute x, and that takes the value of either 1 or negative 1, depending on x is positive or negative. So here are the diffs, and we realize what we need to compare is just those two because the middle two are already equal. So you want x over absolute x to be equal to y over absolute y, in which case we can just rearrange this to get x over y is equal to absolute x over y, which implies that x and y has to be the same sign. And this only happens in the first or third quadrant. So this function is only differentiable in the first or third quadrant, where you're going to have to exclude the origin because it's not differentiable at that point because the partial derivatives are not even defined. Okay, and then holomorphic. So if omega is an open subset of the complex plane, if a function f is differentiable in omega, then we notate it by saying f is holomorphic in omega and using this notation. So a function is homomorphic. If it's holomorphic in the entire complex plane, then we call it an entire function. So something to note is that a function can only be holomorphic on an open set, and this is because differentiability depends on the behavior of neighboring points. And if you have a closed set, then your neighboring points might not be in the set itself, which is why at that point we cannot define differentiability anymore. So differentiable functions has to be, holomorphic functions has to be on an open set. That's an important premise. And if a function is harmonic, then it has to satisfy something called the Laplace equation, which is given by this. So an important assumption of this is just that all of the first and second partial derivatives for this function, u, has to exist and has to be continuous on its domain. And for a harmonic function, we can always find its harmonic conjugate, which just helps to satisfy this, what's it called? Harmonic conjugate, such that you make the function holomorphic when you compose f using u and v. And you can use the Cauchy-Riemann equations here to find its harmonic conjugate. Okay, so let's look at an example. We want to show that u is equal to sine x sinh y is harmonic, and we want to find its harmonic conjugate v. So if you want to show something is harmonic, you just have to verify the Laplace equation, which just entails finding its first and second partial derivatives, and then verifying if they add up to 0. And in this case, if you diff it, keeping in mind that diff of sinh gives you cosh and the diff of cosh gives you sinh, you're going to get this, that this identity is satisfied, and therefore it is harmonic. And then you want to find its harmonic conjugate, in which case we just consider the Cauchy-Riemann equations. So if v is its harmonic conjugate, then we know that v and u has to satisfy these relationships, where diff of v with respect to y is diff of u with respect to x, and same thing for the opposite. So then we can just start by looking at one of these and solve it. So if dv on dy is equal to cos x sinh y, then you can integrate both sides with respect to y and get that v must be equal to cos x cos y plus some function in x, because this is the only possibility to get 0 when you differ with respect to y. And then how can we find cx? Is just by comparing your dv on dx using this v to this dv on dx. So if you diff your function that you just found, you're going to get that this is going to be equal to negative sine cos negative sine x cos y plus c dash x, right? If you differ with respect to x, and you're going to compare it to this expression. And clearly, c dash x has to be equal to 0, which just means that cx is going to be some real constant. And because we want to find any harmonic conjugate, you can just take that real constant to be 0. And here we know that b can therefore just be equal to cos x cos y. Okay, and then the final section before we begin exponentials and logarithms is some introduction into exponential functions. So expz is just defined by this Taylor series as it is in 1b. And some properties include, well, you can actually just verify these properties by plugging it in and doing algebra. But remember that expz is periodic with a period of 2 pi I. Okay, so hyperbolic functions based on ex, we define cosh and sinh using something that we're already familiar with. So we all know this from Math 1b as well. And all of these properties you can also verify by literally just using the definition of cosh and sinh, using expz plus exp negative z over 2, or expz minus exp negative z over 2. Something notable is that if you diff cosh, you get sinh. If you diff sinh, you get cosh, which is very handy when you're, in the previous example at least, whenever you're given functions that involves cosh or sinh. And some properties of hyperbolic sine and cosine is as such. So these are just functions that you might find helpful. You can try proving yourself, but basically cosh is really similar to cos and sinh behaves really similar to sine. So cosh is a even function, sinh is an odd function. This is quite obvious because they're both periodical about 2 pi k. And another identity is just that cosh squared z minus sinh squared z is equal to 1. You can verify this by plugging in their definitions using xp. And finally, we define cosine and sine functions in a similar way. This is also de Moivre's theorem. Some properties include that if you plug in iz to sinh, you get I sine. If you plug in iz to cosh, you get just cos. So these become useful when you're trying to simplify hyperbolic trig and normal trig functions with complex input. And that is basically the basic introduction into trigonometry in 2621. So then we're going to look at logarithms and exponentials. You just gotta press over.
Okay. All right, guys. Today, the next part is logarithms. So, for the sake of time, I'll just be going a bit quickly. So, we just define the principal branch of the logarithm as ln modulus of z plus I times principal argument of z, just definitions. And we define the principal argument of z to take values from minus pi to pi. And the principal log of z is differentiable everywhere except on the negative real axis. So everywhere except that, it's going to be differentiable. We're also going to note that the multi-value logarithm is defined as ln modulus z, but this time we are adding just the regular argument rather than the principal argument. And the regular argument is just principal argument plus some multiple of 2k pi. So that's just definitions. Okay. So this course introduced this log theta notation, and what this means is because our principal log defined our branch cut where it's not differentiable to be the negative real axis, what we can say is log theta has a branch cut of just some ray that is theta from the origin. So in this example, the branch cut would be on this line, and I'll just go rid of it. It would be on this line, and it will not be differentiable on this line. So here, the argument of theta will be between theta going to theta plus 2 pi. And the branch cut would just be this arg theta z equals theta. And note that it's differentiable except on the branch cut, and the derivative is just given as 1 on z. Alright, so an example question of this is, we want to define a specific branch of log such that it's going to be continuous at -1 and has a value of 7 pi I there. So normally, when we're dealing with principal log, we know that at -1, that is where our branch cut is, so it'll not be continuous. So we would have to choose a different branch. So the branch we're going to choose is the positive real axis, because if we choose our branch cut to be here now, that means at -1, it is going to be defined and continuous there. Now, since we want it to be 4, that's why f is going to be differentiable everywhere except for this line. So that's a general way to solve for these log differentiable questions. You just let the inside be on the branch cut, so it's going to be differentiable everywhere except there. Alright, so another pretty common question is we have to find all complex numbers z such that the sine of z equals n. We can simplify, we can multiply e to the I z. And then, as we all know, we can just use the quadratic formula and simplify. And then we're left with this. Note that we use the multi-valued logarithm here. So that means, well, all we can do, since it's plus minus, we can split it into two cases, where it's going to be 2 plus root 3i and 2 minus root 3i. So solving, because this is multi-valued arg, 2 plus root 3i is purely imaginary, so it's going to have an argument of pi and 2. But because it's multi-valued, we're going to have to add a 2k pi next to it. And then we're going to divide by I. That's not an I. Divide by I to finally get z equals pi and 2 plus 2k pi minus I ln 2 plus root 3. And we just essentially do the exact same thing for the 2 minus root 3 case. So this question was just, you just remember that sine z is given in this form, and then you just quadratic formula bash it, and then you solve for z. Alright, so more definitions here. So we define the principal branch of a complex power as E or exp alpha principal log of z. So that means if I have, for example, I to the I, that will be defined as, or if I had the principal value of I to the I, that's just going to be E x p I principal log of I. Now this is all principal value, so the multi-valued function, z to the alpha, is just going to be the exact same thing, except the log is no longer principal value. So when you do turn it into principal value log, you're going to have to add some multiple of 2 pi I. More definitions, the principal branch of z to the 1 over n, we define it as the modulus of z to the power of 1 over n times by exp I arg z. Oh, it's back. Okay. exp I arg z over n. But if z is 0, then we just define z to the 1 over n as 0. Right? So how can we use this question? Sorry, how can we use this definition for this question here? If we have to find I to the 2 minus I and the principal value of I to the 2 minus I, remember that the definition was exp. Well, this time it's going to be 2 minus I times, it's going to be the multi-valued log of I And the multi-value log of I is given by ln I plus I pound 2 plus 2k pi, and then expanding it, we should get this. But if we want the principal value only, then remember that it's going to be the principal log here instead. So we are not going to have a 2k pi, hence we're going to let k equal 0 and the principal value is just minus exp pound 2. All right, now we have another example. We have to find where f of z equals pv square root of sine z is analytic. Now remember that sine z is an entire function, so the only issue that we're going to get, well, the only issue we have to consider is with the square root. And we know that the square root is analytic everywhere except for the negative real axis. So we just have to find z such that we are on the negative real axis, and then the complement of that will be where f is going to be analytic. So here, remember that sine z, which is sine x plus iy, can be expanded into sine x cos y plus I cos x sine y. And to find where sine of z is on the negative real axis, that means the real part of sine z has to be smaller than or equal to 0, and the imaginary part has to be equal to 0. So, considering this part here, for cos x sine y to be equal to 0, either sine of 2 pi. Hence, x is going to be within these intervals here. Now remember that this was only the case that y is equal to 0. So we have to consider the other case where cos x equals 0, which means x is some k pi multiple of pi 2. So plugging that in to sine x, that means sine x cos y is equal to sine pi over 2 pi times cos y, which is negative 1 to the k times cos y. Because depending on what k is, sine pi over 2 plus k pi can either be 1 or negative 1. Since we want the negative real axis, that means this has to be less than or equal to 0. So that means minus 1 to the k times cos y has to also be less than or equal to 0. But since cos is always positive, that means this has to be the negative term here. If for minus 1 to the k to be negative, that means k has to be odd. So if k is odd, that means we can rewrite k as 2m plus 1 for some integer m. Therefore, we can say x equals pi 2 plus 2m plus 1 pi, or 3 pi 2 plus 2m pi. So therefore, principal value of the square root of sine z is going to be analytic everywhere, except for our line segments where we found earlier, and on the vertical lines 3 pi 2 plus 2m pi. Alright, now we're onto curves. Now, you won't be directly assessed on curves, but it's important to know some terminology. So, a curve is just a continuous function gamma t to c, where t is just an interval from a to b. And we just say that the initial point of the curve is gamma of a, and the final point is gamma of b. And the range gamma of t, where t is just in. Now, the important part here, we say it's closed if gamma of a is equal to gamma of b. So what that means is, well, intuitively, it just means our curve is going to be closed. And it's not just going to be open like that. And we'll say it's simple if for any s and t, where s is smaller than t, they're not equal to each other. So what that means is, if it's going to be simple if it doesn't cross. But once it crosses, that means gamma of s cross. But once it crosses, that means gamma of s is equal to gamma of t at this point. So this is no longer simple. And oh yeah, if they only cross at the beginning and end point, then we say, or like this curve here, then we say it's a simple closed curve. or a Jordan curve. Now these curves here, we know that this curve doesn't cross itself, so it's going to be simple, but the initial point and the end points, they're not the same, so it's not going to be closed. This point is closed, but it's not simple because we intersect here. And the last curve is simple and closed because it's not intersecting itself, and well, it's closed because that's like intuitively you can see that it's closed. Some more definitions here. If we have two different curves, say I have alpha, and if I have another curve beta that begins where alpha ended, then I can represent this as the join of alpha and beta. And yeah, this is just technical. And we say the reverse curve is gamma asterisk from minus b to minus a to c, and it's just given as gamma of minus t. So the reverse curve just means if this is gamma, that means the reverse curve would just be going the other way. Now, it's important to know how to parameterize lines and circles. So if I have two distinct points, z0 and z1, and I want to parameterize this line here, well, using our knowledge of vectors, I can say this line is going to be z0. Okay, I can't write. Z0 plus some parameter of this vector, z1 minus z0. So a straight line is just going to be z0 plus t, z1 minus z0 for any t that is between 0 and 1. And you can also sense check, because when t is 0, that means this entire term on the right is going to be 0. So you're left with z0, which is our initial point. And when t is 1, that means we're just going to be left with z1, which is our endpoint. So it makes sense. Now, parameterizing a circle, well, we know that a circle, we can actually represent this as e to the it for t that is between 0 and 2 pi. And radius r, we denote that as r here. It's the modulus. And center z0, you can think of it as we're shifting this circle here to a point z0. So a circle, center z0, radius r, can be represented as z0 plus r e to the it for t that's between 0 and 2 pi. Now, derivatives of curves. So if I have gamma that's a curve, we can actually represent it as gamma 1t plus gamma 2t I. And the derivative is just going to be the derivative of each of its components. And we're going to say it's continuously differentiable if the derivative exists and it's continuous on AB. And we say it's smooth if it's continuously differentiable and the derivative is never 0 for any t that is in AB. And finally, we say it's piecewise smooth if it's a finite join of smooth curves. You know, it's okay. It's okay. It's okay. I don't know what just happened. Sorry, guys. Yeah, so here's a join. So note that C1, C2, C3, C4, they're all smooth curves. And this curve here, which is a join of all of them, we can say that this is piecewise smooth. Now, just more definitions here. We're going to say the length of a piecewise smooth curve gamma is just going to be the integral from a to b, the modulus dt. So if I have gamma is equal to r e to the it here, from t equals to 0 to 2n pi, so that means the length is just going to be the integral from 0 to 2n pi of the modulus of gamma t, which is r I modulus of the derivative of gamma, which is ri e to the it. But since the modulus of I is 1 and the modulus of e to the it is 1, that means the modulus of that entire thing is just going to be r. So integrating r, that just gives us 2n pi r. Alright, now, how do we use all of that? A contour we define as the oriented range of a piecewise smooth curve gamma. Now, oriented range of a piecewise smooth curve gamma. Now, oriented range, we just define it as the range of the gamma, and we're going to be ascribing some orientation to how we're going to traverse a curve. And the general direction is we traverse it anti-clockwise. When we start talking about interiors of curves, so this is my little area here, we normally say we're going to traverse it such that the interior is to our left, hence anti-clockwise. Right, keep in mind that a contour is a range because it's the, how does that happen again? The oriented range, well, a curve is just a function. Alright, now we just have some more definitions, and the thing you should get out from this is whenever you have some complex integral, usually you can just treat it as a real integral that just has a random I in front of it. So if I have f of t equals ut plus ivt, I can just split it up as integral of ut plus I integral of vt. So effectively, when we're integrating from real a to b, I can just take the real part of f of t and just put it on the outside. Similarly, I have the imaginary part, and I can just put it on the outside of the integral as well. Now we have a long list of things you can do, but it's like no different to just real integrals. So if I have functions f and g and h is c to a b be differentiable such that h of c equals a and h of t equals b, that means, well, first of all, if I have this integral, it's just saying, well, we can just split it up normally, take the constants out to the front of the integral. Here, this is just like reverse u sub if I let t equal h of t here. This is integration by parts, and this is saying that the absolute value of an integral is going to be smaller than or equal to the integral of the absolute value. And that's going to be pretty important later. So a way we can use complex integration for some real integral is, notice that cosine of t is just a real part of e to the it. And since e to the t is real, that means e to t cosine of t can just be written as the real part of e to the t times e to the it. So substituting that into an integral and using the fact that we can take the real out, all we have to do is just integrate this part here. And using our normal exponential integration rules, we have the power of 1 plus I on the top. That means we have to divide by 1 plus I. And substituting our bounds from 0 to 2 pi, we get this. But remember, the thing we want is e to the cos t, which is the real part. So taking the real part of both sides, doing some simplifying, and then we get our answer. So that is just a way how we can use complex to do integrals. Now here we have a line integral. Given a piecewise smooth curve gamma, we can define the complex line integral as the contour integral of gamma f of z dz is just the same thing as integral ab from a to b of f of gamma t times the derivative of gamma times dt. And you can think of it as just using a u sub, z, or z sub, z equals gamma of t. Because dz, imagine that's a z, t, gamma dash dt, and if you put that in, you replace z with gamma t and replace the balance from a to b, that means you get that integral. Now I have some more theorems here. if lambda and mu are complex, and alpha and beta are piecewise smooth curves, and f of g be complex functions defined on the range of gamma, and further we let gamma be the join of alpha and beta, then we can say that the contour integral along alpha is just, we can just split it as normal. Take the lambda out and take the mu out and split the f of z plus g of z. Now remember the asterisk meant it was going to be a reverse curve. Well, we defined the contour of the reverse curve just to be the negative of alpha if it was traversed anti-clockwise. So essentially, contour integrating anti-clockwise is just a negative of contour integral going clockwise. Now here, since gamma is the join of alpha and beta, all we can say is the contour integral of gamma is just going to be the contour of alpha plus the contour of beta. So here, evaluate the contour integral of gamma of z squared dz, where gamma is the unit circle. The way you do this is we first have to parameterize gamma. Since it's the unit circle, we can let gamma be e to the it for t that is from 0 to 2 pi, because it's the entire circle. The derivative is going to be I e to the it, and then using our little u sub method, we can just plug it all in. So it's going to be e to the it squared, because it was z squared. It's to multiply by the derivative of gamma t. And then you get 0 to 2 pi, I e to the 3it. And then you can integrate this as if it was just a real integral. Now we have another example here. This time, gamma t is t plus it squared for t that's from 0 to 1. And our integral is the conjugate of z. Nothing different. We're going to be doing the exact same thing. So the contour integral of conjugate of z is going to be 0 to 1, because t is from 0 to 1 here. F of gamma t times gamma dash t. And we're going to be subbing in gamma t and gamma dash t. And then you want to be expanding all that, and then integrate, and then sub in as usual. Now we have reparameterization. So all it's saying is if I have two curves, gamma, a to b to c, and h that is c to d to a to b, and h is a continuous bijection such that h of c is a and h of d is b, then we say gamma composed of h, c, d to c is a reparameterization of gamma. Now the reason why this is important is if we have two piecewise smooth curves where one is a reparameterization of the other, and f is defined on the range, then the contour integrals between the two are going to be the same. So no matter if I say gamma of t is equal to t on 0 to 1, or delta of t is t plus 1 or minus 1 to 0, effectively they're the same curve, so the contour integral both is going to be the same. Okay, now this is where that modulus absolute value comes in with the ML lemma. And this is going to be important much later on. So if I say gamma is a piecewise smooth curve and f is a complex value function defined on the range of gamma, then we say that the absolute value of the contour integral of gamma, f of z dz, is going to be, so if the argument's from 0 to pi, that tells me it's just going to be a semicircle with radius r. So the way we do that, most of these questions, we're going to be using the reverse triangle inequality like we saw earlier. So we know that the modulus of z to the power 4 plus 1 is going to be greater than or equal to z to the 4 minus 1. But since the modulus z is r, and as r approaches infinity, r is going to be greater than 1. So this is equal to r to the 4 minus 1. So that means taking reciprocal on both sides, we have the modulus of 1 over z to the 4 plus 1 is smaller than or equal to 1 over r to the 4 minus 1. Now remember the ML lemma said that this was smaller than or equal to the maximizer times the length of the curve. Since we are just on the upper semicircle, our length of the curve is just going to be pi r. So by the ML lemma, the absolute value of this integral is going to be smaller than or equal to pi r times 1 over r to the 4 minus 1. Now, taking the limit as r approaches infinity, you can see that this approaches 0. Now, this is the question where you're going to see a lot of later on. Anyway, that is it. Now I'm going to be passing it on.
Alrighty. Okay, so I'll be taking the remainder. I'll be taking the remainder of integration up to Morera's theorem. Let me just check out this pencil. Yeah, that's a bit garbage. What about this one? That's even less. Okay, I guess we're gonna use the pink pencil. Okay. Yeah. So what we've been doing up to now has been quite analogous to just regular multivariable, just with like some like imaginary like flavor to it. But once we move on to Cauchy-Gaussat, this is where complex analysis really like comes into its own and really starts the results we get really start to get interesting. And so yeah, let's just begin. So we define a contour integral. We said before that the integral is independent of a reparameterization, right? And so there's no need to worry specifically about the parameterization that we use. So this gamma here is actually not necessary when we can just replace it with the general range that it gives us, which is this capital gamma, right? So we define contour integral as that. Okay, Cauchy-Gaussat theorem, okay? So it says that if omega is a simply connected domain and f is holomorphic on that domain, then if gamma is a closed contour, then the integral is equal to 0. So what does this look like? So just say we've got this is our set, and within this set, this is gamma, like that. Okay. If f is holomorphic both inside and throughout gamma, then the integral is equal to 0. And this is really powerful. And the extension of this is when we have multiply connected domains. So previously, this is just for when there's no holes. We can also have a domain that has holes in it, like this. Oh, okay. Then as long as f is holomorphic on this interior, as well as the boundary in total, including the holes, so this circle, and the outer circle, then the sum of the integral along each independent contour here will also equal 0. And I think that this will make more sense with examples. Okay, so here's a very basic example. We have gamma, here's the unit circle, right? And so we want to integrate this function over the unit circle. Well, if you just look at what this looks like, right? The unit circle is here, and then minus 1 plus I, that would be minus 1 plus I, that would be somewhere there, right? And so actually what we're integrating is holomorphic everywhere, right? Like everywhere that we're interested in, because the only singularity is outside it, right? And so now we can just straight up just use this above one here. We know that this integral is equal to 0. No computation required. Okay. The consequences of Cauchy-Gaussat, the first one is the independence of contour, which should make sense, right? Like if a loop has integral 0, that means going this way has to be the opposite of going this way, right? And so if this is equal to the negative of that, then this has to equal that, right? And so the independence of contour just says when we're in like this holomorphic area, we don't need to worry about what path we take. We just worry about the endpoints. And this leads quite naturally into the existence of primitives, right? Because if we only care about the endpoints, then there should be some way to find this integral only caring about the endpoints. And so this is the complex analog of the fundamental theorem of calculus that we have. And it just has a slightly stricter condition, which is that f needs to be holomorphic. So if omega is a simply connected domain in the complex plane, and f is holomorphic in that domain, then there exists a function, capital F, which, when you evaluate it at its endpoints and subtract them, gives you the value of the integral. Okay, so this is very similar to in like 1a, 1b, except the extended for complex numbers. Cool beans. Yes, and f here is the primitive or antiderivative. Okay, so now we want to calculate this integral. Okay, and we said that gamma goes from I to negative I, and it's completely on the left-hand side of the graph here, right? So if I just to draw that, that means we're starting here, taking some random journey, and then we're ending there. Okay, we want to use the primitives from this previous slide, right? Because we know the endpoints. So as long if we can just find something to plug in, then this will make our day like quite easy, right? And so here we have the integral of z minus 1 on the bottom. Oh, sorry. And dz like this. Oh, you really cannot read that. Right? And so intuitively, we know that the antiderivative of 1 on z would be log, right? That's what we want to use. We want to use logs. The only problem is the principal branch of the logs that we know has a branch cut, right? It has this branch cut over here on this negative axis, which is a problem because we require everything to be holomorphic on the contour that we're using. And so the way we do this is we can kind of just manually pivot the branch cut by using a separate branch of logs, right? So for example, if we use the branch of logs that has a branch cut on the positive axis, well then our contour goes undisturbed, right? And so now we can use the antiderivatives. So that's exactly what we do. We'll define log 0 z minus 1 as the branch that has a branch cut at this positive axis here, right? So r goes from 0 to 2 pi, okay? And when we do have that, this allows us to go here undisturbed through this contour. So we're allowed to use the antiderivatives as long as this antiderivative we use is this new branch of the log 0 z minus 1. And so just applying that, we let f be, we let f be, man, this is, okay. We let the antiderivative be log 0 z minus 1. Then we can just evaluate it at the endpoints and subtract them. So that's what we've done here. And importantly, this I term that we have is different to what we would have done if we used the principal value, right? Because the principal argument of negative I minus 1, that would be in the third quadrant. That would be some negative number, but we can't use that. And so that's where our branch of the log comes in. And yeah, that gives us our answer. Alrighty. The Cauchy integral formula. Suppose that omega is a simply connected domain, f is holomorphic on that domain, and gamma is a simple closed contour. And we have some random w, which is in the interior of that contour, right? This gives us a really nice relation between the integral we're trying to solve and just a point to plug in. And actually, this has a lot of connections to the residue theorem, where we'll get up to tomorrow in the next part. So pretty much, just to try and connect a drawing to this, if we have a contour like this, right? This inside part here, this is holomorphic everywhere except for one point, right? At this W point. So if we're trying to integrate something that is holomorphic everywhere except for one singularity, what this formula tells us is it's actually not that bad at all. All we need to do is just plug in the holomorphic part at that singularity, you know, with this constant here that we also need to take care of. Cool. And so here's an example. We have the circle centered at 0 with a radius 3, right? So this contour will look like this. And we have two singularities here, right, at plus or minus 2. There's one there, and there's one there. That's an issue because our formula only accounts for one singularity. So we need to find a way to kind of bypass this double singularity problem. And the way we do this, we can actually do this multiple ways. The way that we have written here is by partial fractions. Now, note, like, you should know this is also like a pretty slow way, and it's pretty slow and could lead to silly mistakes. But if done correctly, it could solve this quite easily, right? So if we split our integrand into these partial fractions and now integrate it as this sum, well, luckily now what we have here is on the top something holomorphic and only one singularity, right? We only have z equals 2 on this one and z equals minus 2 on this one, in which case we can just apply the integral formula. And now just give us I equals 2 pi I over 4 e squared minus e to the negative 2. You can also use the multiply connected version of the Cauchy-Gaussard theorem. I don't know how well I would be able to draw this with this pen, but pretty much we know from the multiply connected version that the contour around these two things is equal to the sum of these two contours. These two contours, both anti-clockwise. And so if we do it that way, as long as we pick these contours to be sufficiently small, just say, for example, in this contour, then that would only have a singularity at +2, in which case all of this part would be holomorphic, and we can just apply it straight away. And this is actually almost identical to the method that we use in the residue theorem moving later on. It's just kind of disguised a little more. But when we use the multiply connected domains with the integral formula, yeah, pretty much has the same output as just the residue theorem. And this can be extended to when these singularities aren't just simple singularities, right? So here it's just to the power 1, but if it's not, then we can just use a generalized formula, which is the nth derivative of f evaluated at w is n factorial over 2 pi I times the integral with this singularity, right? And yeah, it pretty much works the exact same way as this one. It's just for when we have a power of our singularity. And so a basic example here, z squared we know to be entire, it's holomorphic everywhere. Meanwhile, we have a singularity at z equals pi, and it has a power 3, right? And so obviously this pi is within our ball of radius 4. And so what we do is we just apply the formula. So if n plus 1 here is 3, then n should be 2, right? So we have f2 of pi, 2 pi I over 2 factorial. And then we just simplify, right? The double derivative of z squared is just going to be 2. And so we get this integral is just equal to 2 pi I. Alrighty. Now we're going to go into a little more of a complicated example, and I'll try my best to reason it out with some diagrams. When alpha is between 0 and 1, and by considering a keyhole contour around the positive real axis, we want to evaluate this. Okay. If you haven't seen these before, a keyhole contour is something that looks like this. It's kind of a contour that's made specifically in a way to avoid nastiness, right? You can see here we're avoiding the real axis, so you can assume that we should probably be expecting a branch cut on this real axis that we want to avoid. Okay, so if you have alpha between 0 and 1, that means this x to the alpha minus 1 is actually a root, right? Like it'll be x to the negative something where that something is between 0 and 1. So that's a root. And roots have branch cuts, which is quite unfortunate. Okay, but this is where the keyhole contour comes in, right? So you can kind of assume that we're going to want to integrate over the real line somehow. And so the way we're going to do that is with this contour here. Okay, so I'll split it up into 4. So there's gamma 1, gamma 2, all the way wraps back to gamma 3, and then gamma 4. And we're going to be integrating z to the alpha minus 1 over z plus 1. And can you kind of see, especially for gamma 1 and gamma 3, as we take r to be really, really, really small, like as this goes towards there, and end up covering the entire real axis, which isn't right because this integral here is from 0 to infinity. Cool. Okay. So let's begin. We're going to choose to integrate z to the alpha minus 1 over z plus 1. Over this contour, which we'll just call this entire contour gamma, right? I split it up into gamma 1, gamma 2, whatever, but this entire thing is just going to be gamma. Okay. So if the branch cut here, we want to be on the positive axis, right? Because when the branch cut's on this positive axis, it doesn't mingle with our contour, right? Here, there's a singularity at -1, but apart from that, it's holomorphic everywhere else, okay? So we want to use the branch of the argument, which gives us the branch cut here, in which case we want the arg to be between 0 and 2 pi. Cool. And so we'll use the fact that z to the alpha minus 1 has a complex definition, right? It's the exponent of alpha minus 1 log z. And this is where our branch cut comes into play, because we're not using the principal log anymore. We're using the branch of the log that has the branch cut in the positive real axis. And we'll be evaluating along this contour. So let's begin with the entire contour, right? So for this entire contour, there's only one singularity here, at -1. So we can just use the integral formula, right? Because z to the alpha minus 1 within our contour is going to be holomorphic. And so it's just the z plus 1 part that's problematic. So we can just apply straight up the integral formula. So this gives us 2 pi I, and then we just plug in -1 to the alpha minus 1. And then for complex exponentiation, we use this exponent, right? And so when we do that, right, we have the exponent of alpha minus 1 times the principal, sorry, not the principal log, the log 0 of -1. And we define this log to have an argument of pi at -1. And so this just becomes 2 pi I e to the I pi alpha minus 1. Cool, so that's the overall thing. Now we just need to look for expressions for each individual segment. Okay, so we want to take the limit as the capital R goes to infinity and the little r goes to 0, right? In which case, this gamma 1 and gamma 3 on this positive axis will converge onto the real axis, right? Okay, so for gamma 1, it's like very straightforward, right? We're starting at little r, going to capital R in that direction. So we can just let z be some number like x, in which case we just get the limit as r goes to infinity and r goes to 0 of this contour will give us what we're looking for, right? Because that contour will approach the real axis. And so we have 0 to infinity, x to the alpha minus 1 over x plus 1 dx, just like that. Now for the contour going the opposite direction, gamma 3, it'll be pretty much the same thing, except as we are now approaching the real axis from this direction, the argument will be approaching 2 pi rather than 0, because that's how we defined our log, right? Argument starts from 0 to 2 pi. So this way, the argument approaches 2 pi, and we need to take that into account. And so below the real axis, the argument approaches 2 pi. So when we apply our definition here, right, this log, when we split the log into the argument, right, the argument won't be 0, it'll be 2 pi. So that adds like this extra factor here out the front, okay? Because this just becomes e to the alpha minus, okay, I'm not going to bother. But pretty much if you split up the exponent, you'll find that we get this other factor because log goes to 2 pi rather than 0. And when we account for this and the reverse direction, which just negates the integral, then when we take those limits, we can take this factor out, and then we get the same thing that we wanted. And then this negative is just to account for the fact that we're going left instead of right. Cool. So we've done the two parts that converge on the real axis now. Now we're just looking at circles. And especially like throughout this course, if you see a circle blow up to get really big and a circle like shrink down to get really small, you should be getting like alarm signs ringing that something's going to equal 0 sometime soon. And so what we'll try and do is we'll try and show that along the outer arc, the integral becomes 0. And so for that, we just use the ML inequality. So along the large arc, so this is gamma 2, the modulus of z is equal to capital R. And so we can find an expression which maximizes our integrand, right? Because the modulus of z here is R, and so that'll just be R to the alpha minus 1. And then yet again, using the circle inequality, z plus 1 is greater than or equal to. Using the circle inequality, we can also find an inequality between the modulus of z plus 1 and the individual moduli, and that just gives us r minus 1. And so by the ML inequality, we know that the size of this integral is going to be less than or equal to the maximizer on the modulus, which is this, times the length of the curve. Now, if we look back at our curve, it's pretty much a circle. And when we take the limit as little r goes to 0 and capital R goes to infinity, this would be exactly a circle. And so the circumference would just be 2 pi r. And so what we end up getting is that's the modulus and this is the length, right? This is just r to the alpha over r minus 1, like with another constant. And since alpha here is between 0 and 1, right? When r goes to infinity, this entire thing goes to 0, which is what we wanted. So that's for the big outer arc. For the one in the for the small one, we just use our parameterization. So Z, all the Z along that circle look like R e to the I theta, so dz equals that. And then we just plug it in using the parameterization stuff that we talked about earlier. So this equals this, which equals this. And you'll notice here, as little r goes to 0, assuming that we can exchange the limits and the integral sign, this just becomes the integral of 0, which is just 0 itself. So which tends to 0 and r gets arbitrarily small. Cool. So what we've shown is that these two circles go to 0, while these two go to what we want. So now we can just finish up. Putting it all together and applying the limits, when capital R goes to infinity and little r goes to 0, okay, the first one we said just turns to that. The big circle goes to 0. The second part has this constant at the front, and then the last one goes to 0. And then using the integral formula, we knew it all equals this. So now we can just rearrange. Okay, so this integral that we're looking for here will just equal this. And then using some algebraic trickery and mischief, we can factor out e to the I pi alpha minus 1 from the denominator. And then we have something of something minus its own conjugate, which looks like a sine. And then once you crunch through the algebra, you just get the entire integral is equal to pi over sine alpha pi. How elegant. Alrighty. Another example. Show that if f is entire such that the modulus is less than the modulus of like a k-order polynomial for a positive integer k, then f is a polynomial of degree at most k. If you want to show f is a polynomial, something that polynomials, a characteristic property of polynomials is that after you diff them enough times, you're just diffing 0, right? And it's going to be identically 0 everywhere. So if we can show that if you diff it enough times after k, it'll just become 0 for n is a positive integer, then we can show it's a polynomial. And so that's what we're going to do. So we have this f to the k plus n term. Now, luckily, through the integral formula, we know a way to relate derivatives with integrals, right? Because you just plugging it into the integral formula, the generalized integral formula, we have that it's equal to this. So we just want to show that this is equal to 0. And how do we do this? You guessed it with the ML inequality as well. And so if we choose gamma to be just a circle of radius r, like this, okay? If we just let gamma be a circle of radius r, okay, then we can first look to try and maximize the integrand and then look at the arc length, and then hopefully that should tend towards 0. Okay, so for this bottom numerator part, right, we can just use the circle inequality once again, and then just raise both sides, right? So we get this, which is nice. Oh my god. Yeah, and then for the numerator, we're given in the assumption that the modulus of the numerator is less than something, and so we just apply that. That's this here. Right, so this numerator is less than mod z to the k, and this denominator using the circle inequality is less than that, right? And so once we just replace the mod z's with r's, we get this, right? And so what do we have? We have pretty much r to the k over r to the k plus more. So the bottom r, like the degree of the bottom is larger than the degree of the top, right? And because this is true for all r, then it has to be true as we take r towards infinity, right? And so that's what we have here, right? So if that's the modulus, right, then we can just like attach this 2 pi r term here just to complete the ML lemma. So we have the size of this derivative, okay, is going to be controlled by this expression, right? And here we have r to the k plus 1 over r to the k plus 1 plus n. So as r goes to infinity, this should go towards 0, and hence any derivative above k will always be equal to 0, okay? And this is pretty much the key that allows us to say that it's going to be a polynomial. Okay, because f is entire, then it should have an associated Taylor series, right? And the coefficients of these Taylor series are just its derivative. But if its derivative just becomes 0 after a while, then this Taylor series is just a polynomial, right? And so, which is only, since f is entire, we can represent a Taylor series, which only has non-zero terms up to the kth power. This means f must be a polynomial of at least, at most degree k. Alrighty. Now for the last part, we've got Liouville's theorem and Moreira's theorem. Liouville's theorem is actually quite surprising. It says if f is bounded and entire, then it has to be constant. So there's no holomorphic function like that's defined on all of the complex plane that doesn't go out to infinity. And Moreira's theorem, it feels like just the converse of Cauchy-Gaussat. Is pretty much saying if f is continuous on omega, which is a domain, and every possible closed contour within omega yields an integral of 0, then f has to be holomorphic. If you remember, the Cauchy-Gaussat said if f is holomorphic on gamma, then any integral over a closed contour will also be 0. Cool. So here is a pretty nice example for Liouville's theorem. So if f is an entire function that satisfies this property, then f of z equals f of z plus 1 equals f of z plus I for all z, show that f is constant. Okay. Now, if you want to use Liouville's theorem here, and we want to show it's constant, if we look back at the conditions, we want to show that it's bounded and entire. Well, it already gives us that it's entire, right? It's right here. So something about this requirement needs to tell us that it's bounded. Okay. So what we have f is periodic. If you go f is periodic if you go left and right, because if you add 1 and subtract 1, it's the same. And it's periodic if you go up and down, right? In other words, let's hope this diagram doesn't fail on me. If I were to draw a 1 by 1 square here, right? Can you see how the entire behavior of our function is dictated by its behavior on this square, right? Because if it repeats every 1, that means something here will be the same as something there, which is the same as something there, and so on. And the same, if it's periodic every I, then something here would be the same as something there, which is the same as something there. So in other words, this one tile actually like tiles the entire plane because it's a repeating unit, right? Because this function is periodic in both directions. Okay, so what about this tells us that it's bounded? Since f is periodic, its behavior on the complex plane can be described fully on the set S given by this, which is just this one square that I talked about, right? Now, we know that f is entire, which means it must be holomorphic, right? And if it's holomorphic, that means it has to be continuous, because we know differentiability implies continuity. So if it's continuous on here, right, and beyond it, right, that means it can't blow up to infinity, like plus or minus infinity, right? The only way a continuous function can blow up to infinity is if we're like utilizing the entire domain, right? But here it's just like a small set, right? So if it's continuous on here, then it can't blow up to infinity, and so f can't diverge to plus or minus infinity. So in this little s here, we know that it has to be bounded. Okay. Oh my god. Okay, so we know it has to be bounded on that one tile. And then from there, the intuition might start to kick in. Well, if it's bounded on that one tile and every other tile is just a repeat of that one tile, then it has to be bounded everywhere. But how can we write that mathematically? Almost there. Right? For any z in the entire complex plane, right, pretty much we can choose integers m and n such that z minus m plus in is in this one first tile that we chose, right? It's pretty much saying no matter where we are, we can always find some analog within this tile S such that f of z is f of z minus m plus in. Hence, if f is bounded on this one tile S, then it must be bounded on the entire complex plane. And then now we know that it's entire and it's bounded, so by Liouville's theorem, it must be a constant. Just a cheeky little remark, this like logical reasoning that we use here, that if it's holomorphic, then it has to be bounded, it ties into something, I don't think it's in the course, it's the maximum modulus principle. But apart from that, yeah, if it's, if it's bounded and entire, then by Liouville's theorem, it has to be constant. And I think that wraps it up. That was the last example. We've somehow finished on time. So if I could just remind you guys all, if you haven't already, please scan the attendance form to mark your attendance. Yeah, give you some time. Wait, not done, we're not done. And just another reminder, because it's really important. 2026 peer mentoring. It's happening next year. Next year at the start. It's the structure of it is pretty much you as a mentor get paired with like some other mentors, and then you get some mentees, right? And your job there is just to kind of make them feel at home. It's like you're just there to like you have weekly activities and bondings, and it's a great time for everyone, right? It's great to just this is your chance to be a friendly face, right, for the next year high school students. I highly recommend. So yeah, be a peer mentor. And I think that is the end. Thank you. Am I in the street? Am I in the street? Am I in the street? What button?
Okay, first, turn off the.
Oh my god, that iPad was actually rage bait.
My bad.